Last time we talked about how to multiply, add, and subtract polynomials. Today we're going to look at some kind of shortcuts for multiplying and expanding stuff out, multiplying out bunches of polynomials. And specifically, we're going to look at binomials, binomial expansion patterns, and some other, and one other product pattern that we already know about, right? If we multiply conjugates, you guys already know that a plus b times a minus b, or the flip of that, right? If I commute those, I get a squared minus b squared. It's difference of squares. No big deal. You're very familiar with that one. I just wanted to remind you about that. We'll look at maybe an example or two possibly here towards the end of that, but you've already seen a bunch of that. What about stuff like this, though? This is different. What happens? How would you deal with something like a plus b squared? What would you do at this point? I bet I know what you do. Yeah, you just multiply a plus b times a plus b and FOIL it out, right? Okay, what if you had a plus b cubed? Well, a plus b times a plus b times a plus b, right? Okay, that's a little bit more of a hassle, isn't it? Because you have to multiply things in pairs, right? So you'd have to multiply the first two together, get an answer, simplify it and get an answer, and then distribute again and multiply by the third binomial, right? Well, what about a plus b to the fifth? Yikes. That's a lot. That's going to take you half an hour, probably to do. I mean, look at this. You got to multiply all this whole thing out in pairs. So what's that mean? Well, we've got to take those two, multiply them together, get an answer, right? There's already a little bit of a problem. Then I've got to take that whole thing, whatever that answer is that I get from this guy, and multiply that times another a plus b, right? Expand the whole thing out, collect like terms, go through the whole process, and then I've got to take that answer and multiply it by another one, and so on, and so on, and so on. That's pretty time consuming, right? It'd be nice if there were a shortcut way to do this, and there is. There's a little mathematical structure called Pascal's triangle that bails us out here. So first, let me explain how you build Pascal's triangle, and then we'll talk about how to use it, okay? So Pascal's triangle, it's just a pyramid-shaped mathematical object, no big deal. You start with a 1, and then these are kind of the rules. You guys can build it for me here. As we move down from row to row, so we're starting off, and instead of calling it row 1, we actually call it row 0. We're starting at 0 just like a number line, and then we're going to go to the right from there. But in this case, we're going down from there, right? You'll see why. All we do is any number, and they're covered up by boxes, any number is going to be built from the numbers that are above it, right? So later on, like if I'm looking at that number right there that we're eventually going to have, it's going to be the sum of the two numbers above it that feed it, okay? The ones on the edges of the triangle, though, they're only fed by one number from above, and it's always going to be a 1, isn't it? So what's that number there going to be? It's going to be 1, right? Everybody see that? Because the only number above it is that 1 right there, right? What's this number going to be? It's going to be 1. Yeah. Okay. What's that number going to be? 1. Yeah. You get it? Okay. That one's 1. What's that one? 1. Getting boring. Okay, what's that one? At least we get a little difference. That's 2. Yeah, good. Okay, so that one and that one are both 1. Okay, what's that one going to be? What's that one there going to be? 3. And that one? Are you starting to see? Do you think there's going to be some symmetry to this? Looks like it, doesn't it? It looks like all these rows, whether I go from left to right or right to left, would have the same pattern, wouldn't they? Right? Agreed? Because there's a symmetry to this thing. The pyramid is going to develop, or the triangle is going to develop the same on the left as it does on the right, isn't it? Right. Okay, so those are both 3s. Now let's see what this means. Okay, what does this thing mean here? Well, we'll keep going with the triangle here in a second, but let's just pause and look at what an individual row means. Well, what row 3 really means here is it's telling us what would a plus b to the 3 expand out to be if I were to multiply that whole thing out, okay? It's telling me what the coefficients would be when I went through this whole long process of multiplying it out, binomial times binomial, get an answer and do it again, etc. If I did all that work and collected like terms, this is telling me what the coefficients would be in my answer. The first term would have a coefficient of 1. The second term would have a coefficient of 3. Third term would have a coefficient of 3. Fourth term would have a coefficient of 1. Okay, that's what it tells me. So a plus b cubed, because that's the row number, a plus b cubed, is going to be this. Now, what gets attached to those coefficients? What are the numbers 1 and 3 and 3 and 1 being multiplied by? Well, here's how we build up the other part of each term. What are they being multiplied by? Again, the row number is 3, so the exponents of the factors in each term always have to add up to 3 because it's row 3. We start off with the entire exponent being shifted over to the factor a. And as we walk from the left to the right through those terms, by the time we get to the right term, all of that exponent has been shifted over to be attached to the b instead of the a. In the middle, it's incrementally going to always, as we move from left to right, from term to term, the power of the factor a is always going to drop by 1 as the power of b increases by 1, so that the sum of the two always stays 3 though, right? So the first term, it's 1 a cubed b to the 0. We don't even write the b to the 0 part. Plus, next term, 3 is the coefficient, a squared b to the 1. Look, the a dropped by 1, the b increased by 1. Next term would be 3. Now the a drops to a to the 1. The b increases to b squared. And then finally, the last term is 1b cubed. See how it works? Okay. All right, so let's build this table up a little bit more, just Pascal's triangle, and then we'll use it to maybe answer a bigger one. Okay, so what's going to go there and there, right? So we got those two are 1s. What goes there? 4, and then that would be 4 also, right? Those are 4s. What goes there? 6. Okay, and then that's going to be obviously a 1. Those are going to be 5s, right? Those two are both going to be 10s. Agreed? See how it's working? Okay, and then everybody agree that would be the next row? Okay. Okay, so then what's that tell us? Well, we get some important information. Well, first of all, the row 2 and 3 expansions we use so much that we just want to memorize those. Okay, like we just did row 3. Okay, there's row 3. A plus b cubed is a cubed plus 3a squared b plus 3ab squared plus b cubed. Okay, we want to memorize that one. A plus b quantity squared. We do that all the time. That's a really easy one to memorize, but we want to use that one too. Well, that's row 2, where the coefficients are just 1, 2, 1, right? So what's that one going to turn out to be? A plus b squared is 1 what? A to what power? Squared. Yeah, good. Squared. Okay. Plus my next coefficient was 2. Yeah, a to the 1, b to the 1, so just ab, right? Plus 1 what? B squared. Okay. Give me 1 to 5. Does that make sense? Okay. How we doing? Okay. All right. Good. 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 So then what if I wanted to do a plus b to the 5th? That was going to be pretty ridiculous, right? But now we have a way to do that without having to go through all that work. We just build Pascal's triangle real quickly, and then we'll use it. Okay, so what does row 5 tell us about a plus b to the 5th? Johnny, what are my coefficients going to be? 10. I better give myself a little more room. Huh. Okay, and what are we attaching to that? So those are my coefficients. Mackenzie, what are we going to get? Like, what's going to be attached to that 1? A to the 5th. Okay, good. Plus, what's going to be the next one? Go ahead, Miranda. What's the next one going to be? What did we do before, right? We said we're going to always drop the power of the A's, which is the first, right? A to the, started at 5. 4. There you go. Good. So A to the 4th times to the what? They have to add, they always have to add to 5. So B to the 1st. There you go. Good. And we wouldn't even write first, would we? We'll just make that one kind of invisible, but it's there, right? Agreed? Okay. Next one. Maylin, go ahead. What's that one going to be? 10. Good. A cubed. Good. Okay. Next term. What's that going to be to us? 10. There you go. Okay. Next one, Abby. There you go. Okay. And last one. What's that going to be, Kenzie? Well, okay, so we already did A to the 1, right? So yeah, so the B is going to go to what power on that last one? No, remember the B's are always increasing by 1. They started at 0, 1, 2, 3, 4. So now we get B to the 5th. There you go. Is that what you said? Okay. And then the A is to the 0, so we don't even write it, right? Because remember, anything to the 0 is just equal to 1. So we're just multiplying by 1. So we just get our B to the 5th. I think you were saying that, and I just wasn't hearing you. Okay? Good? All right, there's another additional piece here that kind of helps a little bit with this too. If you look at some patterns in Pascal's triangle, we get some really cool patterns showing up. Notice that if we look at the first diagonal is kind of the first ascending diagonal. So from left to right, it's going up, right? So the first ascending diagonal is just a bunch of 1s. That's boring. But the next one, what do you notice about the next ascending diagonal, which just contains the second number in each row, the second coefficient in each row? What do you notice about that? It goes in order, and look, they line up with the row number, right? Well, the row number is just giving us the power of the binomial that we're multiplying out, right? So we know, for example, in this last one, like we know that guaranteed it's A plus B to the 5th. And so we know that the second coefficient has to be a 5, right? That's kind of helpful because we know that if we do A plus B squared, if you ever forget that that's a 2, well, it's got to be a 2, right? Because it's A plus B squared. So the second coefficient has to be a 2. Here, the second coefficient must be a 3, right? It's pretty easy to fill in the rest, okay? All right, so let's try this then. What if we, and here's just another picture of Pascal's triangle. Same thing, okay? Okay, if we wanted to do A plus B to the 8th, I mean, that would take forever to do, but look, there's the coefficients to make that happen, right? Let's just do the first few terms of that. I just want to make sure everybody's got this. So what's the first term going to look like? Okay, it's going to, coefficient's 1, right? Good. And what's going to be attached to that? A to the 8th. There you go. A to the 8th plus, what's the next one going to be? 8. And we knew it had to be an 8 without even looking at that row because of that, right? What are the powers going to be there? B to the first. Good. Okay. Plus next one. There you go. Okay. A to the 6th, B squared, and so on. We won't do the rest, but you guys get the idea now, right? Okay. And that's going to be, man, that's a long one. Lots of terms in that one. Okay, so there are some kind of cool things that pop out of this. You notice that if you do some things to Pascal's triangle, you start to see some interesting patterns, right? Like if I take all of the coefficients and I'm going to kind of tilt this triangle, so I'm going to squish everything over to the left and line up vertically each of the coefficients. Then you can build some diagonals that give you an interesting sequence. Look at this, like you've got, if I add up diagonally here, I get a 1, a 2, a 3, a 5, an 8, a 13. That looks pretty random, but have you guys ever heard of that sequence before? Those are just the terms in what's called the Fibonacci sequence. Raise your hand if you've heard that before. Is that a number or term you've ever heard? No? Maybe you've kind of heard in a movie. Okay, yeah, it comes up a lot. Now you can build it another way too. Let's see, let's do it this way. So really you don't include 0 in it. You start with 1 and 1. And the next term is a 2. How do you think I get that? 1 plus 1 is 2. Okay. What do you think the next term is? No? 3, because you're always adding up the preceding 2. So that's a 3. What's the next one? What's the next one? What's the next one? Etc. Right? And it keeps on going on and on and on forever like that. Okay, big deal. Well, the Fibonacci, this is just, it's almost eerie that it works this way. But nature, for some reason, really prefers the Fibonacci sequence. Like if you look at daisies, for example, at different types of daisies, right, that have different numbers of petals, you find that the number of petals in daisies, in various daisies, it's always just follows the Fibonacci sequence. You'll find one type of daisy that has 2 petals, one that has 3. There isn't one that has 4, but there's one that has 5. There's no 6 or 7, but there is an 8. It just works like that. If you look at what are some other examples? Like if you look at the bottom of a pine cone, and try this sometime. If you pick up a pine cone and you look at it from the bottom, you'll see that there are groups, the way that the scales are distributed on the pine cone, you'll see that you can create kind of like little arcs that are formed that start in the middle and fan out. And if you go from, what's that? Go on a field trip. Maybe, okay, when the weather's nicer, maybe we'll go find one here like later. There's some pine trees up on the side. We'll try that. But it's, if you count these things, if you go clockwise around the base of the pine cone and you look for the number of these little patterns, little rainbow patterns where you can see they're really distinct, you'll always find that it's a Fibonacci number. And then if you go the other way, if you go counterclockwise, you'll also see patterns where you can see these little kind of distribution, these little rainbow shapes where the, I don't know how you do, what you haven't described it, evil, like these little, I don't know, it almost looks like a fan shape or something, You'll find that if you count those, almost always you get an adjacent Fibonacci number. So it might be something like in one direction it's 8, in the other direction it's 13. It's crazy. You can do the same thing with sunflowers. If you look at the face of a sunflower and you start in the middle, you can see these fan-shaped growth patterns with the seeds in the sunflower. And again, if you look clockwise and you count them, you'll get one Fibonacci number. You go the other way, you'll get an adjacent Fibonacci number. It's crazy. I'll look for some pictures maybe at the end here when you guys are working, so I can show you what that looks like. But you find all these things. You find all these crazy number patterns that mathematicians use. You know, powers of 11, triangular numbers, tetrahedral numbers, powers of 2. You can find all these things in Pascal's triangle if you just manipulate it the right way. So it's interesting. All right, but let's practice a couple concrete problems here. How about something like, what if I wanted to expand out 2x plus 10 quantity squared? What would I do? Well, I'm going to use row 2 in Pascal's triangle. That's the expansion I'm going to use, right? That's one we got to remember. What is a plus b quantity squared equal to? A squared plus, oh, I got to have a 2 there, right? Plus 2ab plus b squared. Okay, and you see how you can kind of just make that up as you go, right? That's an easy one. One other thing I'll also point out, let me backtrack just slightly here. If I go back to this, here's our Pascal's triangle. How many coefficients are in each row based on the row number? If I know the row number, I ought to be able to predict how many terms there are going to be in that expansion, right? Like row 1 has 2 terms, row 2 has 3 terms, row 3 has 4 terms. What would row 1020 have? How many terms? 1021, right? There's always going to be one more term than the row number. So when I'm trying to remember what the heck x or a plus b quantity squared is, all I've got to do is know, okay, well, if the row number is 2, there's 3 terms. First one has a coefficient of 1. Second one has to have a coefficient of 2. The last one's got to be 1, right? It's got to be symmetrical. I can just kind of reinvent that every time I need to. And before you know it, you just have it memorized. Okay, how does that help us here? If I want to figure out what the quantity 2x plus 10 squared is, how does that pattern help me? What's acting like a and b don't show up here? What am I substituting for a? 2x. Everybody see that? A is just going to be whatever the first term is. What's b? 10. Yeah. B is just 10, and I'm just going to follow my pattern, right? So I'm going to get, what's this going to be? Well, I'm going to get the quantity 2x squared plus 2 times a, well, a is 2x, times b is 10, plus b, which is 10, squared. See how that works? And then I would just have to, simplify that. What does that work out to be? Well, what is the quantity 2x squared? 4x squared, right? Because I'm going to square the 2 and square the x, right? So that gives me 4x squared. What's 2 times 2x times 10? 40x. There you go. And 10 squared? 100. There you go. Okay, you get the idea? Okay, so a lot of times textbooks they'll have separate patterns for a plus b squared and a minus b squared. That's a waste of brain cells. You don't need to do that. Save those brain cells for more important things. You don't need that. All we have to do is use our a plus b pattern, but now what's a this time? What's b? -1, right? Subtracting 1's the same as adding -1, right? Okay, so then we could just write this one as my a squared is going to become the quantity. Let's change color so we can see the difference here. I'm going to get 10x quantity squared plus 2 times a, which is 10x, times b, which is -1. Everybody get that? Plus b, which is -1 squared. So when I simplify that, what is the quantity 10x squared, everybody? 100x squared. Okay, now you got to be careful with this one. What's 2 times 10x times -1? Okay, good. So I get a minus 20x and negative 1 squared? 1. Okay. So you can kind of see what's going to happen here. When the second term is negative, I'm just going to always alternate from positive to negative to positive. If it were a bigger expansion, I would have had another negative term and so on. Just alternates then. Okay? Let's try another one. How about, let's try that one. 10x minus 9 cubed. Okay, so we got to remember what row 3 is. You can make this up though. How many terms? 4. Okay, what's first term? That's easy. A cubed. Okay, next term, what's the coefficient? 3. There it is, right? It's going to be 3. So plus 3 a squared b. Next term, coefficient? It's got to be 3 because it's got to be symmetrical. Same if I'm going left to right and right to left, right? So plus 3 ab squared, and then finally plus, there you go, 1b cubed. There you go. Okay, we got it. So now all we got to do is just apply that pattern with these values for a and b, 10x and negative 9, right? Okay, so remember here now we've got a is 10x, b is negative 9, right? Because really I've got a plus in the middle there, 10x plus negative 9. Okay, so what's that giving me then? Well, I'm getting my a cubed. So that's the quantity 10x cubed plus 3 a squared. Well, that's 10x quantity squared, right? Times b, which is negative 9 plus 3 times a to the 1. Well, that's just 10x times b, which is negative 9 squared, plus b, which is negative 9 cubed. Okay, give me 1 to 5. Does that make sense? Okay, and then all I would have to do now is just simplify that out, right? So what is the quantity 10x cubed? Yeah, 10 cubed is 1,000. And then x cubed, well, that's easy. That's just x cubed. Okay, how about this one? I've got 3 times the quantity 10x squared times negative 9. Let's multiply these in a convenient order. What's 3 times negative 9? Negative 27 times 100, right? Because it's going to be a 10 squared. What's negative 27 times 100? Yeah, negative 2700. Just add 2 zeros when I multiply by 100, right? And then what's the power of x going to be? Yeah. Okay. How about this one? Now I've got, let's see, I've got negative 9 squared is 81 times 3 is, I'll tell you, that's 243. But if I multiply that by 10x, what do I get? I'm going to add a 0 and then multiply by x, right? And then finally, what's negative 9 cubed? Anybody know what 9 cubed is? I think it's on there. Yeah, okay, so I'm going to get a minus 729, and we got it. Okay? So yeah, that's useful, isn't it? Man, how much time does that save us?